All right. Welcome to another member seminar. It's a true honor to have one of our very internationally well-known members, Professor Nicolai Reshetikhin, who is going to talk about integrable systems and representation theory, life at the interface of geometry, algebra, and analysis.
Hello, can you hear me? Okay. So, so this is the title, and of course, as usual, I'll be talking about something different. So, actually, so here's the plan of the talk. So first, I will explain what an integrable system is. I think many people know this, and I think many people know it in sort of in different ways. So we just want to make it uniform. And then at the end, I will describe some of my favorite projects. You know, to describe completed projects is meaningless because you can all go to the archive and to see sort of the papers. So I'll say a few words about the projects, ongoing projects, and about things that I would really like to do. So first of all, there are many ways to think about integrable systems. The very traditional way, and I think that's my personal opinion, that's the correct way to think about integrable systems, as integrable systems in Hamiltonian mechanics. So first, let's fix notations. So phase space of a Hamiltonian system, it's a term, is a symplectic manifold, let's say 2n-dimensional, and symplectic manifold, it's a smooth manifold with a two-form attached to it. That's the symplectic structure on the manifold, such that it's closed, d omega is 0, and non-degenerate. One way to think about non-degeneracy is just to write in local coordinates form using the matrix omega ij. Non-degeneracy means that the determinant is not vanishing. And this condition doesn't depend on the choice of local coordinates. So then a very important algebraic way to think about symplectic manifolds is the following. Once you have this two form, since it's non-degenerate, you can invert it. And you will get a bivector field. So you get a Poisson bivector field, Poisson tensor. So this matrix is just the inverse to the matrix of the form. And then you can define this bracket between functions, smooth functions on M, which is the bivector field omega inverse evaluated on the two form df wedge dg. In local coordinates, it's just this. So then it's a standard exercise for people who start studying the symplectic geometry is that the closeness of omega is equivalent to the Jacobi identity for this operation. So we have a Lie algebra on the space of functions. This Lie algebra is given by first-order differential operator in each of the variables, and so it satisfies the Leibniz rule as a consequence. And so actually, it's a very interesting algebraic structure. It's a commutative algebra, as usual for algebra functions with pointwise multiplication. It's a Lie algebra structure on the same vector space. And then the Lie algebra structure acts by derivations on the pointwise multiplication. So it's sort of conceptually, it's the next step after commutative algebra when you have this extra structure. Okay, so now Hamiltonian dynamical system is the following. So every dynamical system is just a differential equation given by some vector field, if it's a dynamical system on a smooth manifold. So Hamiltonian dynamical system is given by the vector field that's generated by a smooth function. Since we have this bivector field omega, so omega inverse, so we can pair omega inverse with one form dh. As a result, we have a vector field. And so that's the definition of Hamiltonian vector field, and trajectories of the Hamiltonian system generated by this function h are flow lines of the Hamiltonian vector field VH. In other words, they are solutions to these nonlinear differential equations, and that's the picture of the flow lines. Okay, so that's the standard thing about Hamiltonian dynamics. Now, these differential equations can be very complicated. And as we know, there is a whole subject in analysis, the study of differential equations, various properties of differential equations. That's the analysis. The question is, can we actually use geometry and algebra to solve these nonlinear differential equations? It turns out, yes, but they must be very special. And so the way how I will explain it now kind of separates two things. Integrable Hamiltonian dynamics, where you can solve differential equations, and the tools that allow you to solve these differential equations. So the most important tool is, okay, it's this structure on the symplectic manifold. It's the fibration over some n-dimensional smooth manifold such that every generic fiber is a Lagrangian submanifold, which means that if you will take your symplectic form restricted to each generic fiber, it's zero, and also Lagrangian means the dimension of this fiber is maximum possible with this condition. So this vanishing means that it's isotropic. Maximal dimension means it's Lagrangian. This is a very important class of submanifolds in every symplectic space. And another algebraically, this means the following: that how can I? Okay. So this is like driving some complicated thing. So Lagrangian property of fibers means that if you will take a function, if you will take functions on the base, pull back to functions on the symplectic manifold, then this commutative subalgebra in the algebra of functions on M is also Poisson commutative. In other words, Poisson bracket between any two such functions is zero. So this is, I would call that this is an integrable system on a manifold. And here's an example of it that you typically find in textbooks. So suppose that you have n independent functions, which are Poisson, pairwise Poisson commuting. So then this setup is simply given by level surfaces of these functions. The projection is just the base is a region in Rn, which is the region of possible values of these functions. And the projection is just maps point x to the value of every function hi. So that's very typical. And of course, globally, you can think of this h1, hn as local coordinates on the base. Okay, so then there is a theorem that's known as Liouville-Arnold theorem. Sometimes it's yeah. Anyway, so this it's known as Liouville theorem. It's known as Liouville-Arnold theorem, and then there is some third name sometimes. Whatever. So the theorem is the following: generic fiber of such vibration is always isomorphic to its generic fiber. There are some singular fibers. I will say more about this. It's always isomorphic to the product of some plane and a torus. And if it's compact, then it's a torus, and these tori, they are known as Liouville tori. So then the other thing is, in local coordinates on the base, I will, according to this example, I will call these local coordinates h1, hn. So local coordinates, they generate commuting vector fields on the coordinate neighborhood, just as in this example with Rn. And then multi-time flow. So you have n vector fields, they all commute. So you have n commuting dynamical systems. So you can combine this all into n times. So you have the multi-time flow with n times. And the theorem, the second statement of the theorem is that the times of these flows generated by the Hamiltonians, they form a local affine coordinate system. Affine means that coordinate transformations are linear transformations and translations. So if you choose Hamiltonians in a different way, this H1, Hn, you will have different. Oh, okay. So then you have different times S1, Sn, and the coordinate transformations on the fibers, they are affine. So it's linear transformation omega plus the shift eta. So that's the second part of the theorem. And the third part is that these times and the values of the Hamiltonians, they form so-called Darboux coordinates. In this setting, they are known as angle action variables. These are local coordinates, but they have this wonderful property that the symplectic form has this special form. So this is the integrable structure. So I just want to emphasize again that you have this Lagrangian fibration, kind of almost Lagrangian in the sense that only generic fibers are Lagrangian. And as a consequence, you immediately have this Liouville-Arnold theorem. So then the question is, what is the integrable Hamiltonian dynamics? Intuitive meaning is clear. So a dynamics is integrable if you can solve differential equations. So if you are very good in analysis, you can use analytical tools and solve these equations. Usually it's very difficult. Using analysis, you can prove the existence and some other things. And usually, once you have the existence, you have to press the button of a computer and then have numerical results. That's very universal. That doesn't require exact solutions. So we are dealing with a very special situation when actually using completely different set of tools, you can describe solutions. So intuitive meaning is that you can solve equations of motions. The geometrical meaning of an integrable Hamiltonian dynamics is the following. So suppose that you have your favorite Hamiltonian H. You want to study the trajectories of the Hamiltonian vector field generated by H. And suppose we have an integrable system, this Lagrangian fibration that I just described. So then here is the definition. The Hamiltonian dynamics generated by the Hamiltonian H is integrable if this projection projects all flow lines to a point. So in other words, if the dynamics is going only fiber-wise. So in these local coordinates or global coordinates, in case of this example that I mentioned before, this simply means that the Hamiltonian Poisson commutes with this special functions H1, Hn. Okay, so immediate consequence of the Liouville theorem is that if the Hamiltonian dynamics is integrable in this sense, then flow lines are straight lines in the angle coordinates. And that's a great news. That means that we solved the problem explicitly in the sense that if you are very clever in algebra and geometry, if you constructed these angle coordinates, so then basically the problem is solved. So then if you can, so then here is the answer. It's just all you have to do is you have to make a coordinate transformation back to the initial coordinates. So, but life is more interesting. I mentioned that only generic fibers are required to be Lagrangian. So, so here's an example of a harmonic oscillator. So it's a function on R2. In this case, it's a symplectic manifold with the standard symplectic form dp dq. The Hamiltonian is p squared plus q squared. These are the level curves of the Hamiltonian. You can see that generically it's a circle, but then there is a very singular one at the beginning, at the origin. That's the zero-dimensional Liouville torus. And we will see that in more complicated examples, that's exactly what happens. And this is kind of expected to be happening. Afterward, just wait. So now I want to describe another example. This is too simple. This is harmonic oscillator. Okay, go ahead, ask your question. No? Yes, a conceptual definition. But then there are technicalities related to. So yes, so conceptually, integrable systems are those systems where you don't have to use the analysis to solve differential equations. So now I'm describing an example, a very special example known as the Kalodjera-Moser-Sutherland system. So, oops. Yeah, so let's consider the cotangent bundle to the special unitary group. So this is the group of unitary matrices with the condition that the determinant is 1. So then matrix elements Gij of these matrices, they are kind of almost coordinates on SUN. If it wouldn't be SUN with the condition the determinant is equal to 1, if it would be UN, this would be coordinates on an kind of, again, almost, but really almost coordinates. So now natural coordinates on the cotangent spaces are Pij such that the form, symplectic form is given by this simple expression. So the special condition means that the trace of matrix P, sorry, it should be Pii equal to 0. And, you know, so the result is that we have even dimensional symplectic manifold of dimension twice times the dimension of SUN. In other words, 2 times n squared minus 1. Okay, so then it's well known that the cotangent bundle to any Lie group is any finite dimensional Lie group is trivial. So so here we can trivialize it, say, by left translations or by right translations on the group to the cotangent bundle at the identity, which is exactly the special unitary matrices, which can be regarded as just Hermitian n by n matrices. And so as a result, our symplectic manifold is given, is just simply the product SUN dual times the group. And then if we will introduce, you see, the problem with these coordinates P is that they are coordinates on the cotangent space at the point G. But now this SUN dual is the cotangent space at the identity. So we should translate coordinates P to the identity. This translation is given simply by this matrix multiplication. And then between this coordinate function, between the coordinate functions x and g, we have these Poisson brackets. So this is the usual Poisson brackets on the dual space to SUN. And this is how they kind of assembled together with G. So then, you know, it's a very simple exercise from here to see that if you will take traces of powers of x, these functions Poisson commute simply because these are Casimir functions for SUN. So then we have multi-time flow generated by those functions. This is not an integrable system because we have only n-1 such independent functions, but the dimension of the space is much bigger. It's 2 times n squared minus 1. But still, we have this commuting multi-time flow. And it's very easy to see that it can be solved explicitly. I just will show this flow. So the functions. Okay. So the functions are given by traces of powers of x, and then if you will compute what it means, this expression, you will see exactly that you can solve them in this way. So it's because x commutes with itself, so this is really commuting flow. And now I want to explain the idea of the projection method in this, the algebraical tools that are used in all integrable systems, starting from Korteweg-de Vries equation to Sine-Gordon equation, and in all finite dimensional cases. Either this or some modification. So the idea is the following. In your symplectic manifold, you choose a submanifold, which is preserved by this multi-time flow. This is step number 1. And step number 2, you try to find the symplectic manifold S such that you can project from M to S, and this dynamics that is symplectic at the top, it remains to be interesting symplectic dynamics, Hamiltonian dynamics at the bottom. So, okay, so then as a result, you will have some algebraic description of the Hamiltonian dynamics on S. This is the answer, and then you project it to S, and that's all. So this procedure is known as the Hamiltonian reduction. And I will describe it exactly how it works in this specific setting. So typically, this submanifold M is coisotropic to those who know symplectic geometry. And the projection from M to S is the symplectic reduction of the coisotropic submanifold. So this whole thing is known as the Hamiltonian reduction. And so that's the kind of the main idea, is that take the simple flow on some kind of standard symplectic manifold and then do the Hamiltonian reduction. The equations become nonlinear, but still using this formula for the Hamiltonian reduction, you can obtain solutions by a completely different set of tools, by algebra geometric set of tools. Okay, so here's the implementation of this idea in our SUN case. So let's consider the action, the action by conjugation of SUN on itself, and let's lift it to the natural action on the cotangent bundle. So in our case, after the trivialization, so now we trivialized it into SUN dual tensor SUN cross SUN. So that's the action. And then it's very easy to see that this action Hamiltonian with the moment map given by this formula. I'm not going to explain what exactly it means, so I will explain the consequences of these words. So the consequence is the following. If you fix a coadjoint orbit in the dual space to the Lie algebra into SUN, so it's just coadjoint orbit. So then the pre-image of this orbit with respect to the moment map in the cotangent bundle is preserved by the dynamics that I described before. And if you take the quotient of the pre-image over SUN, that's a stratified symplectic space. So this is a new word, stratified symplectic space. Before, I was assuming that all symplectic manifolds are nice and smooth. In real life, most interesting symplectic manifolds are not nice and smooth, but there is an intermediate class before they become really horrible. It's the it's the spaces that are stratified by smooth symplectic strata, and then with natural agreement on where the strata meet. So you see here you have for every coadjoint orbit you have a submanifold. Here, this is symplectic. This is actually coisotropic. And then you have the projection mapping. Projection means taking the quotient with respect to the SUN action. And the result is this stratified symplectic space. If you don't like these words, if you're not ready for them, think of this as a symplectic manifold. That's not going to be a terrible mistake, because these are symplectic manifolds that are stratified in such a way that there is a big open stratum of the full dimension, and then there are small pieces, small low dimensional pieces that are glued. So, you know, as a first approximation, you can ignore this stratification and just work with the smooth large dimensional component, which sort of most of the people in this business are doing. So this is the Hamiltonian reduction, the symplectic reduction of the cotangent space to SUN via the coadjoint orbit O. So as a result, you have this symplectic space pre-image of the orbit mod G. Okay, now let's look at our specific example, and let's do some very simple computations. So the moment map, as I described before, it's just x minus G inverse xg. And so our symplectic manifold, our symplectic space is just the following. You take this space of pairs x comma g from this Cartesian product, and that satisfy this condition, that this combination of x and g belong to the orbit O, and then you mod out this whole thing by the action of SUN. Now, as I already said, that this space is actually stratified symplectic manifold in the sense that there is a big stratum, smooth stratum, and then there are low dimensional pieces glued to it. So let's not pay attention for the time being to the low dimensional pieces. The big stratum is just the space where element G has different eigenvalues. So that's an open dense subset over there. It's easy to see that this thing is isomorphic as a symplectic manifold to the cotangent bundle to the regular part of the Cartan. Regular part of the Cartan is just exactly the diagonal matrices that satisfy this condition, gamma I is not equal to gamma J. Cartesian product with the Hamiltonian reduction of the orbit with respect to the coadjoint action of the Cartan. So these are two symplectic manifolds. You take the product with the product symplectic structure, but then you do something slightly nasty. You consider the orbifold. You quotient it by the action of the symmetric group. So I was lying when I said that it's a smooth manifold, but it's a smooth orbifold. But I forgot who. I think Ezra Getzler taught me that once you see the orbifold, treat it as a smooth manifold. You will never make a mistake. Okay, so I'm following his advice. Yes, so the claim is that the dynamics that I described before, it projects to the Hamiltonian multi-time dynamics on this reduced space. So, but remember that in this multi-time Hamiltonian dynamics, we had n-1 times. So n-1 independent Hamiltonians generated by this, generate these dynamics. You see, the dimension of this space is twice times n-1. That would be great if we wouldn't have this piece. But this piece gives some extra dimensions, and we have to figure out what to do with this. So first, yes, that's what I wanted to say. So, this dynamics is integrable when you have when the dimension of the orbit is 2n minus 2, then the Hamiltonian reduction is of this orbit. It's just a point, and the dimension of this regular piece is 2n minus 2 again. So this is a classical work of Kasdan, Kostant, and Sternberg from the 70s. And then what to do if the orbit has higher dimension? Well, it turns out that there is something that's called superintegrability. And actually, this particular system is superintegrable for any orbit. Okay, so let's first consider this Kasdan, Kostant, Sternberg example when the orbit has rank 1. It has dimension, in this case, 2n minus 2. The Hamiltonian reduction with respect to the action of the Cartan is a point. You see, the Hamiltonian reduction works like this. When you just quotient, let's say, take GIT quotient of the orbit with respect to the action of this group, the dimension drops by the, if there are no stabilizers, the dimension drops by n minus 1, the dimension of the Cartan. If you do the Hamiltonian reduction, the dimension drops by twice the dimension of the group. So in this case, the dimension will be 2n minus 2 minus 2n minus 2, 0. So that means that it's a point. So in this case, the regular part of the orbit is the orbit itself. So there is no stratification. So it's just this orbifold. So natural coordinates are H regular is just the collection of circles. So natural coordinates is Qi. Q is between 0 and pi. And then you have Pi on the cotangent directions. And the condition that Qi is not equal to Qj. So then X is traceless. So that means that the sum of p's is 0. Then if you compute the second Hamiltonian, you will see that it's wonderfully can be interpreted as n one-dimensional particles. This constant c is determined by the orbit. The orbit is zero-dimensional, it's a point, but there is actually one parametric family of such orbits. So this c, and then you see you can interpret now this as an n one-dimensional particles. And then if you want to compute high integrals, then there is a simple formula for this. The SUN condition means that the sum of these coordinates is 0. So the dimension of the phase space is 2 times n minus 1. So it's a model that's known as Calogero-Moser Sutherland model. Calogero, Moser, they invented this model without the sign, just Qi minus Qj squared. Sutherland introduced signs, and then there is a long, beautiful history of integrable models of this type. So it's been known that this value, can you see everything here? No, it's. Which doesn't work. Okay. Anyway, so it's been known that these points are very special. There is a long history about this, but no, don't break. Okay, super, bravo. So what we proved as an exercise is that actually these points, they are this point. This is a fixed point. Sorry, I made it plural, but it's a single point. It's actually a fixed point of this multi-time evolution. So then with Guru and Mai and with the same company of people, so we did a complete classification of low dimensional, this singular Liouville-Torre. It turns out that for every k, there is a singular Liouville-torus. And then there is an interesting story that sort of partly was motivated by this previous result, the story of hybrid quantum classical systems that I'm not going to talk about today, but let's just separate. I think I gave several talks on this already. So so let's look at another example. So suppose that now we take not these special rank 1 orbits, but let's choose generic orbit. So in this case, we have the regular part given by this formula. W is the symmetric group, is the Weyl group for SUN. And then the second Hamiltonian, instead of the constant here, has these variables, functions on this quotient space, on this Hamiltonian reduction of the orbit. So again, you can interpret it as n particles with this funny potential and with this funny spin variables. This is why it's called spin-Kalogero-Moser system. And again, the higher Hamiltonians are also, there is a simple formula. So then, actually, that's the paper that is coming for more than a year. I think Cheng Zhou gave a talk just before this talk. I don't know. He is here. He's probably recovering from his talk. So anyway, so with him, with Jiang and Xiao, so we proved the following thing, that this flow, it generates a stratified superintegrable system. So basically, there is a stratification at every step there. And it's very interesting because I confess that I wrote several papers before on this spin-Kalogero-Moser systems, never paid attention to the fact that actually everything is stratified. And what's interesting is that if it's spinless Kalogero-Moser, if there is a constant here, then you can see that if you started your trajectory when, at the regular point when Qi is not equal to Qj, the trajectory can never go to the point Qi is equal to Qj, simply because that's where the energy is infinite. So because energy is a conserved quantity, this Hamiltonian, so it cannot go to the boundary. In the spin case, what can happen is that Qi is equal to Qj and mu ij is 0. So actually, the system with good choice of initial conditions, it actually goes to the boundary. And so this is why you cannot ignore this stratified structure. Okay, so so that's some of the recent results and published and unpublished. I think all of these results are unpublished. So, so then there is a nonlinear version. You can replace the cotangent space, cotangent bundle to G by the modular space of flat connections on a torus with one puncture. Then on such torus, you have two cycles, let's say A and B cycle. And then if there is no puncture, then there is a condition, the product of, then the group commutator is 1. If there is a puncture, there is no condition, so this space is isomorphic to G cross G. And the, well, from a T and bot, we know that this space has a natural Poisson structure. And so this Poisson structure is a natural deformation of the symplectic structure that exists on T star G. So, so then there are natural generalizations. You can consider any surface with any number of punctures. There are some superintegrable systems there. So the stratification for this system is unknown. It's a very interesting problem. So then if you will do the quantization of such things, if you're interested in quantizing such systems, a lot of things is known about quantum Kalogero-Moser systems. they are related to special functions, to harmonic analysis on SUN. This is just so there is like a huge continent of this work, and this is just one village on this continent. So we did some work with Jasper Stockman on this subject. So but the point is that none of this. So what is the precise meaning and the nature of stratification in the quantum case is not clear. People haven't been focusing on this. And that's something that's related to representation theory. You know, this spectrum of, in this particular case of the Topology system, the spectrum lies in the positive part of the Weil chamber. And you already know that it's a cone with generic points inside and special points on the boundary of the Weil chamber. So there must be something special there, but this is not completely clear. And then you can make a nonlinear version of this by quantizing moduli spaces. So there's this. So that's, I'm very much puzzled by all this. Okay, then some other favorite subjects. So I understand that the goal of this talk is basically to introduce myself. So I'm introducing myself. So actually, my favorite subject is not finite dimensional systems. This was just an exercise, but infinite dimensional systems. So you know, there is classic, neoclassics, modern, postmodern, and so on. So postmodern is probably artificial intelligence. So the classics is in this subject, it's the integrable partial differential equations. Korteweg-de Vries equation is very famous. To the chain where the space dimensions are discrete and time is continuous is another example. The beautiful phenomena there is the solitons, the solutions that propagate without changing the shape, quasi-periodic solutions that are obtained by algebra geometric methods, a kind of triumph of algebraic geometry in dynamics, where you can actually solve nonlinear PDEs using the methods of algebraic geometry. And then the neoclassics is, well, you can, roughly speaking, by deforming T star G to this modular space, you can deform to the chain to relativistic to the chain. Again, there are two solitons there, algebra geometric solutions. So, and there is a very interesting subject in geometry and algebra, so-called cluster variables and cluster coordinates on various algebraic manifolds. So something that's not being explored, I think, in all these directions is the infinite dimensional cases. So it's been known since you know, early works on solitons, in particular, you know, by Kyoto School, by Sato and Jimbo, Mila, and others. George Wilson wrote some interesting papers on this. So this infinite Grassmannian, but then one of the ingredients of this infinite Grassmannian is GL infinity. On GLN, it's known that there are cluster variables due to Fomin and Zelevinsky. So exactly what it means for GL infinity, it's a very interesting open problem. So how the stratification is working in the infinite dimensional case, how the superintegrability is working in the infinite dimensional case. So this whole realm of problems is a very interesting one. And then another universe that I didn't touch on is what happens in the quantum version of this. This is 1+1 dimensional quantum field theory, which is integrable. And you know, if I'll start to talk about this, we'll stay well after dinner. So then related to number 2, there is number 3, that's integrable models in statistical mechanics. There are basically, they come in 2 big groups. One big group is Damer type models. These physicists would call these free fermions. And the other type of integrable systems come from representation theory of quantized affine Lie algebras. So these are the 6 vertex models and similar to this. This is a very interesting, fascinating subject known as integrable probability nowadays. But it has long roots in statistical mechanics, in many other things. So then there is a very traditional, you see, my 2 teachers, first was Popov and the second teacher was Fadeev. For those who knows the quantization of gauge theories, you know that there is a Fadeev-Popov gauge fixing technique. So I was always puzzled what exactly is this. I never paid attention to it. I was obsessed by these integrable systems. And then at some point I thought it's a shame. I have these 2 great teachers and I don't know what they did. So I started to study it and then got kind of involved into the BV versions of quantization of gauge theories, and kind of so we had this series of papers with Alberto Cattaneo and Pavel Mnev, so where we developed the analog of Batalin-Volkovitsky gauge fixing for space-times with boundary. The simplest case is just consider the time interval across the Euclidean space. But it doesn't have to be this way. It can be more complicated. So then, one of the toy models in this business is the Poisson sigma model with Lagrangian boundary conditions. That's what I want to do. That's the Poisson sigma model. It appears in in constructing of star products. Am I over time? A little bit. Okay. So I'm almost done. So it's a topological 2-dimensional field theory. It's fascinating because it has a gauge symmetry, but this gauge symmetry is not given by the action of a gauge group. It's just given by some vector fields that form a Lie algebra on solutions to the Euler-Lagrange equations, but outside they don't. They're just some tangent distribution. So it first appeared in So Kontsevich constructed his famous star product for quantizing of Poisson manifolds. So here's the problem. Let's say M is symplectic or Poisson. You consider smooth functions on M. Consider formal power series in some variable h, the Planck constant. And then what you want to do is you want to construct a star product such that it's a commutative product in 0 order. In the first order, it's Poisson bracket, and then formal power series in H. So this problem is known as deformation quantization. So there is a long history there. Bronstel, Plato, Sternheimer, they kind of initiated this this work, and then there is a kind of flow of steady flow of work in algebra, in homological algebra, kind of sorting out various algebraic techniques, whether such product exists for symplectic manifolds or not. And then Kontsevich came, and he just constructed an explicit example of such star product and gave a full classification of these star products. The answer is the following. For a Poisson manifold, equivalence classes of such star products are in bijection with formal deformations of the Poisson tensor. So the way how he did it is the construction starts with some very explicit formula for a star product, for a single star product. And then Cattaneo and Felder, they noticed that his formula is just Feynman diagrams for this nonlinear Poisson sigma model. So since we were talking about integrable systems, here's a very specific problem. I would love to see the solution to this problem. So the problem is the following. Classify all star products for which there exists a star commutative subalgebra deforming given integrable system. And second, classify all such deformations of this given integrable system. So in other words, you have a classical integrable system, construct all possible formal quantizations of this system. Conjecture is that for any star product, such subalgebra exists. And then for a given star product, the space of deformations of such algebra modular equivalences is just a space of deformations of this Lagrangian projection modular natural equivalences. So that's a conjecture. And then it should be the extension of results of Kontsevich and Catania-Felder. And what should be different is the choice of Lagrangian, choice of boundary conditions in this nonlinear Poisson sigma model. So these are all the toys, and here is the serious business. So there's this beautiful result by Yao a long time ago about the positivity of energy in the gravity. So then, Lars, please be very critical at this point. This is a pure speculation and wishful thinking. So the fact is that there is a nice classical Hamiltonian framework for gravity. If you reformulate Einstein gravity into the Palatini-Cartan formulation. For the Einstein gravity, there is no good Hamiltonian kind of once you have a boundary for your space-time, then Palatini-Cartan is not equivalent to Einstein. So then the question is, so what is the analog in this Hamiltonian framework of Yao's results, and how to kind of put this? This is all infinite dimensional. So one should somehow develop the appropriate infinite dimensional setting for the symplectic manifolds. And then the question is whether the notion of energy exists in this setting. This is not going to be asymptotically flat metric, but a metric with given boundary conditions. So that would be very nice. And again, so that's sort of for adults, and for children there is a toy model. Toy model of the four-dimensional gravity is two-dimensional gravity. So that's when it becomes conformal Liouville conformal field theory. I searched the literature and was trying to find a good Hamiltonian framework for the Liouville theory on a surface with boundary, and it doesn't exist. So it's even at this setting. So once you start to have surfaces with boundaries, space-times with boundaries, many things should be re-evaluated. Okay, so that's all.
Okay, questions for Nicolai?
Yeah, so thanks for a very interesting talk. So for this last slide, I mean, that's actually I mean, as you probably know, I mean, this is a large subject, actually.
Yes, this is why I hope
and people have indeed tried to formulate, you know, look at the Hamiltonian formulation of Einstein theory in the presence of boundaries. And I mean, many people like Kiosky and his collaborators. Yes. And also more recently, there have been a number of conferences on this topic. And there is a real problem in the sense that, you know, the Einstein-Cauchy problem is well posed. You have global uniqueness and so on. But once you introduce boundaries, the notion of, you know, unique evolution starts to become problematic, and you have to think about how can you pose boundary conditions and so on. And that's a very, very subtle problem.
Right, I completely agree.
Yeah, yeah. And it's a worse problem than in ordinary field theories like Yang-Mills and so on, where you can treat these things. But in Einstein gravity, you have to think of there's this local global aspect to the theory, which is caused by the constraints having an elliptic nature and so on.
Right.
And of course, this is then somehow connected to the idea of quasi-local energy and stuff like that, which has been interesting Yao for many, many years. There is not only the Schoen, Yao, Witten, work on positivity mass, but later on, Yao has been, and many other people have been pushing this question of, is there a quasi-local notion of energy can energy be localized in gravity? In other field theories you have local notion of energy, but in gravity there is no such natural notion. There is no stress energy tensor.
Stress energy tensor doesn't exist because G is a dynamical field.
Yeah, and so this is very much connected to this, and much of the work on this problem, on this type of situation, has been driven by those kind of questions. So, yeah, I only a comment.
No, thank you very much. So maybe I'll just one more comment and question. So there's this old framework which we rediscovered, but then we correctly attributed it. I think that he was a teacher of Kiosky, Tulchiyev. Yes. So. Yes. Yes. So. So the kind of the idea is that, especially in the first order framework, which is exactly where Palatini-Cartan appears. So basically, there is a symplectic structure on the space of boundary fields. And for this, the space-time doesn't have to be a cylinder, it can be anything. Then you ask, what is the natural boundary condition? The natural boundary condition is a Lagrangian submanifold in the symplectic manifolds, because the boundary value of Euler-Lagrange solutions, they form another Lagrangian submanifold. And then correct boundary condition is when you have Lagrangian submanifold boundary conditions intersecting Lagrangian submanifold Euler-Lagrange equations more or less generically, say ideally by one point. Then this is the solution with these given boundary conditions. So I'm wondering if people in gravity try to do this. Okay. So Lars, we have something to talk about.
More questions? So is it true that, naive question, any parameterizing space, any space whatsoever, is locally always induced by an integrable system, algebraic integrable system locally? Any manifold, any stack, any moduli stack?
Well, you have to have symplectic structure.
You always can have that.
Okay,
as long as this space parameterizes homologically defined.
Yeah, you see, this complete integrability is a global. That you can do it globally. Locally, you can. It's.
And then second question.
It's this theorem from differential equations.
And the second question is, you said in this infinite dimensional case, I was actually wondering, at least I'm not working on this, but how do you even do Hamiltonian reduction for infinite dimensional spaces?
There are various, well, you see, then you have to be delicate in the sense that if you go all the way into making everything precise, then you will be so precise that you will have no room to move around. So you always have to kind of leave the option to make everything precise at the next step. So, so then one way to deal with these infinite dimensional manifolds, there is something, say, in field theory. How can I? Yes. So when you working on infinite dimensional variational problem, if your functionals are local, then there is a very nice tool that's called variational bicomplex. Mm-hmm. So basically, if your functionals are local, then you do some kind of variational theory, and you develop this kind of de Rham theory in the direction of fields and the direction of the manifold only locally for jets of functions.
Right.
And then it's sort of easy to make sense of it.
Locally.
Once you start to globalize it, this is a big business and it's a complicated theory. So for these differential equations, again, there are, say, for example, for GL infinity, there is a version of the Lie algebra GL infinity, where you have only finitely many entries. That's a nice version. It's the inductive limit of GLNs, but it's not very interesting. You can have finitely many off diagonals. That's a very interesting one, where the Lie bracket is defined, but there is a non-trivial central extension, and then there is a million of others. So basically, it's the brave new world, these infinite dimensional things. There are many ways to define an infinite dimensional object, but there could be two different infinite dimensional objects that are kind of simply different topologizing of the same problem.
More questions? If not, let's thank Nicolai again.